Okay, so now we're going to be taking a look at the 6.7 material. This deals primarily with a little bit of stuff with integer exponents and our scientific notation, which is the big part that we're going to be covering in our second half of this section. So we have one more property that we need to cover in a bit more detail with the 6.7 material, and that's working with the negative exponent. We worked with this a little bit in 6.5, we at least saw a glimpse of it, but we are going to be expanding on it and seeing it in a bit more detail and a few other examples here first and foremost before we go on to our scientific notation, because this does show up quite a bit. So zooming us in here, I just want to make sure we have this visible. So looking at a negative exponent, what that looks like for us. So if n is an integer and a is a non-zero number, that's what this part means, then a to the negative n power is the same as saying 1 over a to the negative n. And the same thing can, or similar one can be stated if we have 1 over a to the negative n power, then that result is going to end up being a to the n. This is an expansion on the quotient property that we got from section 6.5. We're going to go through some examples of this, and I think the very subtle but understandable mistakes that people have when they're working with negative exponents. We'll see some examples of that here down below. And this warning is the big one with all of that. A negative exponent does not inherently change the sign of its base. Again, a negative exponent does not inherently change the sign of its base. So that means if the base of the negative exponent is a negative, that doesn't necessarily mean that the negative exponent is going to make that negative base a positive. It might, but you cannot jump to that assumption. The negative in a negative exponent moves the base to its opposite location in a fraction. That is it. You could also think of it as the negative in an exponent only flips the fraction you are working with. It does nothing to the signs. That has everything to do with the actual number of the exponent, not the sign of it. So we'll take a look at what we mean by this with a quotient to a negative exponent property, and then we'll go into some examples of this and what this is going to look like. So with this, we have a quotient to a negative exponent. If a and b are real numbers, and a is a non-zero number, b is a non-zero number, and n is an integer, then if I have the quantity a divided by b raised to the negative n power, that's equivalent to saying the quantity b divided by a all raised to the n power. So as I mentioned up here, negative in the exponent moves the base from its to its opposite location in the fraction, which means the negative in this exponent just flips the base. That is all the negative in the exponent does. Now right down here, the negative in the exponent flips the fraction. That's it. It does nothing else. It does not inherently make the answer positive. It does not inherently make the answer negative. All the negative in the exponent does is flip the fraction. That's it. There's nothing else from there. So we'll go through a couple examples of this because I do want to show you guys and see what these do look like in practice. So I'm going to reference these 4 examples over on our Blackboard. I'm going to do a couple examples or some extrapolations from our first one that we have here, but this is where I'm going to be drawing our examples from as we jump over to our Blackboard and go through a couple examples with this. Okay. Oops, there we go. Okay, so our first example that we were given, there we go. Okay, so our first example that we were given was working with simplifying these answers, the problems we've been given. So our first problem that we have is written out as 3 to the negative second power. So as with all exponents, we need to correctly identify the base of that exponent so we know what number, what numbers, variables, anything like that are being affected. So in this case, It's just the number 3. Now, for me personally, there's lots of variability you can go in with this. I like to first look at what can I do with that negative in the exponent part. So what's my base? It's 3. So what does that negative in the exponent part do? It flips that fraction. So that 3 is implied to be a 3 over 1. It's one of these other invisible ones that hangs out with these numbers. So the negative in the exponent, all that does is flip the fraction. So before you apply that 2 that's there, just flip this fraction and make it 1 over 3 to the second power. We've gotten rid of the exponent, or the negative part of the exponent, I should say. And from here, now I am just left with a positive exponent, and I can work with this. So 3 to the second power, that's going to give me 9. So I get 1 over 9. That's my final answer. So again, we need to make sure that we are working specifically with what's the base, and then the negative only flips the base. That's all it does. It does no other inherent changes to any of the values, any of the signs, any of that. All the negative in the exponent does is flip the fraction. That's an example of this. So kind of deviating from our notes here just a little bit, making up another example. If we have negative 3 to the negative second power. So again, as we had with all exponents, correctly identifying the base. What is the base of this negative 2 as an exponent? Well, the base is just the number 3. It does not include the negative sign out front. So that negative sign would just be along for the ride. And I am flipping the base, which again is just 3 over 1. So I flip that base. That's how I am applying the negative in the exponent. And I get negative 1 over 3 to the second power. And now that negative out front is just going to stay there. 3 to the second power is 9. 1 up top is staying as it is. So I get, for this answer, I get negative 1 over 9. And then lastly, let's say we have the instance where we have negative, the quantity negative 3 to the negative second power. Now we're saying what is being encompassed as the base of this exponent? Well, in this case, it is everything inside of the parentheses that's being raised to this negative second power. So that means everything inside the parentheses needs to be flipped. Instead of being the numerator spot, the entire thing needs to go into the denominator spot of this fraction. Because I flipped it, which is fine, I'm going to get rid of the negative. I'm going to leave the 2 there for now. So my first step, I just want to eliminate that negative exponent. Now that I've done that, now I can apply the number attached to it. So the quantity negative 3 to the second power, that's the same as saying negative 3 times negative 3. And negative 3 times negative 3 is going to give us a positive 9. Get our answer here. So again, make sure when you are going through these, you are correctly identifying what is the base of the exponent, because that is absolutely critical with all of these. And then determining if I have a negative exponent attached to it, how do I just flip that base? If it was in the numerator spot, it goes to the denominator spot. If it was in the denominator spot, it goes to the numerator spot. Just flipping that fraction, or flipping where the base is in that fraction. A couple ways you can think on that, or think about that. So let's take a look at our second example from the notes. So our second example has us starting off with 1 over 4 to the negative third power. So again, what is the base of this exponent? And the base of this exponent is 4. So a negative exponent says I'm going to take the base and I'm going to move it to its opposite spot in the fraction. Or you could think of it as I'm going to flip this fraction. So getting rid of the negative in the exponent first, this is going to become 4 to the third power. Again, that base of 4 was in the denominator spot of the fraction. To get rid of the negative exponent, I am moving the base to the numerator of the fraction, just the opposite spot that it was in. The negative in the exponent is now gone, and now I have 4 to the third power. I can just apply the calculator if we need to do that. 4 to the third power is going to give us 64 for our final answer. So while it's not required that you do things in this order, I generally tend to find, for me personally, that trying to work with or determine, do I want to cancel out or do anything with my negative exponent first? I like to look to that first. So I don't have to worry about, did I flip this? Do I not flip it? How do these numbers interact together? I like to get rid of that before I do anything else with these problems. When you're going through and solving these things, it's your choice on whether you want to do it in that order or a different one. But I've found for myself that that's very, very helpful to do that. Again, essentially try and do these problems in parts, not do all of it at once. So example number 3, we're dealing with the quantity negative 6m divided by n, all raised to the negative second power. So here we have a quotient to a negative exponent. So we're going to use that property. So first and foremost, I'm going to apply the negative of the exponent. And the negative of the exponent just tells me whatever my base is, I'm going to flip that fraction. So instead of having negative 6m over n, applying the negative in the exponent, I just flip the fraction. It becomes n, or negative n over 6m. And now the negative in the exponent goes away. Leaving the 2 there, because I'm going to deal with that here in a second. But I want that negative in the exponent gone. That's all I've done in my first to second step. Now I have the quantity negative n over 6m raised to the second power. The base of this exponent is everything inside the parentheses. So if you wanted to, you could write this out into expanded form. There's nothing wrong with that. And then solve this thing out. Or you could apply any of our previously learned properties to help you go through this. Either option works. So expanding it and multiplying together, I have a negative times a negative, which means my answer is going to be a positive. So that's good. I have n on top in the numerator spot times an n on top again. So n times n is going to give me n squared. For the denominator, 6 times 6, that's going to give me 36. M times m is going to give me m squared. And then I'm looking to see, can I cancel anything else out from this? I'm not seeing anything that I can, so I'm done. So I'm going to move us over, and we'll go through our 4th example from this section. So I have negative quantity 1 over 7 to the negative second power. Now again, here's an instance where I have negative showing up in multiple parts of this problem. I want to determine what is the base of the exponent, work with the negative exponent first, and then apply the rest of the exponent after that. That's my personal thought process with going through these things, and I found that to be very, very helpful with compartmentalizing this thing and doing it in pieces. So the base of this exponent of negative 2, the base is everything inside the parentheses, which means the negative sign out front of this entire problem is not going to be directly affected by this exponent in any way, shape, or form. So it's just along for the ride. Now, applying the negative sign of the exponent to our base. The base is 1 over 7. Applying the negative means I'm going to flip the fraction, and that's it. So instead of being 1 over 7, if I flip that fraction, it's going to become 7 over 1, which is also the same as just saying 7. I've applied the negative part of that exponent, which means now I'm just left with an exponent of 2. From here, I'm still identifying what is the base of this exponent, and that's that 7 inside of the parentheses. The negative out front is not a part of the exponent. It's not a part of its base. It's just along for the ride. So now, what is 7 to the second power? 7 times 7 is going to give me 49. And again, the negative out front is just along for the ride. It's not being affected by the negative or the exponent in any way, shape, or form. So it's just along for the ride there. We got our final answer of negative 49 for this problem. So these are a couple examples of using negative exponents and the quotient to a negative exponent property. So I'm going to jump us back to our notes here. And the last thing I will note that since we have just gone through how we can work with the negative exponents, with these properties with negative exponents, no polynomial final answer may contain negative exponents in it. All must be written to have positive exponents. So that means if you need to start flipping things around, putting something from the numerator into the denominator and vice versa, you now have to do that for your final answer. Everything has to be positive. No negatives anywhere else in there. So if you're looking for, I think this is a really, really great and handy page for this, a summary of all the integer exponent properties that we have can be found in the textbook on page 766. I'm also making a quick summary of all of these right here. If you'd like to take note of those, write those down for yourselves. These are all very, very, very useful. You will be using these on the homework. You will be using these on the test. I promise you that right now. So again, we're assuming if a and b are real numbers and m and n are whole numbers, then we have, again, all of our properties that we went through for this section in this chapter. So we can and will be using all of these at our disposal to solve problems, which we're going to go through some examples of down here. It should be noted that as we're going through even these 4 examples, you will find there are multiple ways to solve these things. I'll show you guys a couple of them as we're going through these, but it should be noted that there are multiple ways to get to these final answers. As long as you are using these properties correctly, you can, it's your choice on which ones you would like to use and when as you're going through this process. So we're going to take a look at these 4 examples. I'm going to jump us over to our Blackboard and we're going to go through those now. So move us down here. So our first example that we have, and we are told with all of these, simplify the following. We're going to assume that all of our bases are non-zero numbers, so we don't have any worries of dividing by 0 or anything like that. So for this problem, again, we're told to simplify. We have multiple options at our disposal. We have x to the negative 4th times x to the 13th. Couple options you can go with. The bases are the same and they are multiplying together. So we could use the product rule to add these exponents together. So using the product rule with this, the bases are the same and multiplying. The exponents will add together, just like we have here. So negative 4 plus 13, that's going to give me x to the 9th power. We have our answer. Alternatively, I'll just go through one of these because there are a few others if you wanted to use them, but these are the main ones. Alternatively, you could say, all right, well, I'm starting with x to the negative 4th times x to the 13th. I want to get rid of that negative exponent before I do anything else, and there's nothing wrong with that. So let's apply the properties of that negative exponent. The base of the negative 4 is x. So I just flip that x, and it's going to become 1 over x to the 4th power times x to the 13th power. If I multiply these two fractions together, remember that anything is implied to be over 1. If I multiply these fractions together, I multiply straight across. I get x to the 13th over x to the 4th. And now, applying the quotient property, if the bases are the same and they are dividing, then the exponents will subtract. So x to the 13th minus 4, 13 minus 4 is 9, I get x to the 9th power. Same answer that we had from our first method. So as you were going through these on the homework and on the test, there are multiple methods, there are multiple ways you can go through and solve these things. You're not constrained to only using this one singular method. If you find one that works really well for you, especially with negative exponents, go ahead and use it. There's nothing wrong with that. But also don't be afraid to get creative and try this method, try that method, try this property, try that property, anything like that. So our second example that we have is 2b to the 3rd power, all raised to the negative 4th power. Now again, you have multiple options on how you could go through and solve this thing. This is, technically speaking, a product to a power. It's our third bullet point that was listed on the notes that we have. We also have a negative exponent. You could apply the negative exponent property first and then work with everything else from there. Multiple options. All of them work. We just need to pick one and then move forward with it. So I'm going to select for this problem, I'm going to apply the negative property of the exponent before I do anything else, because I want to get rid of that. This is my personal preference of doing that. You could use something different. So what is the base of that negative 4 exponent? It is everything inside of the parentheses. So all of that is going to go from the numerator spot to the denominator spot of our fraction. So writing that in, it's like we have right there. So once I flip that, the exponent is now positive, and now I can work with a product to a power rule. So with that, 2 to the 4th power, that's going to give me, I believe that's 16. And then b to the 3rd power, raised to the 4th power, that's going to be using the power rule. So an exponent raised to a power, that means the exponents multiply together, and I'm going to get b to the 12th power. I can't do anything else from here to simplify or cancel anything else out. So from there, I am done. Taking a look at our third example that we have. Again, it should be noted, I'm just doing this so we can keep moving on. It should be noted for number 2, there are multiple ways you could solve that, just like there are for number 3 and number 4. So for number 3, we have x to the 7th power divided by x to the negative 3rd power. And again, multiple options on how you want to solve this. You could get rid of the negative exponent first and then work with it from there. You could instead leave this as I have the quotient of two bases. So I have x to the 7th divided by x to the negative 3rd. The bases are the same and they are dividing, which means if we use the quotient property, we could rewrite this or solve this out to be x to the numerator minus the denominator. And it is crucial that we write in that negative 3 inside of parentheses, because what happens when we have a negative times a negative, it's going to become a positive. So really, with this, I have x to the 10th power. Let me work through it that way. Now again, alternatively, I'll just give you one other alternate method here, because this one's a pretty quick one. Let's say you wanted to take that x to the negative third from the denominator and put it in the numerator spot. Get rid of that negative exponent. You can do that. So if I rewrote this, x to the 7th is just along for the ride. That negative third, its base is x. That means that x is going to go to the numerator spot. Everything is multiplying and dividing, so it would still need to remain as multiplication. And then I get x to the third power. So x to the 7th times x to the third, that's using the product rule then. The bases are the same, and they are multiplying, which means the exponents will add together. So x to the 7 plus 3 is going to give me x to the 10, same thing as I got the other method. And again, there's multiple ways you can go about solving this. This is just a couple of those methods. And on the test or on the homework, I am perfectly happy with whichever one you would like to use. It's your choice. Taking a look at example 4. We've got more things going on now, which is nice because it means we have more options in some regards. Okay, so our fourth example, we have the quantity 3x to the negative 5th, y to the 7th, times the quantity negative 4x to the 4th, y to the negative 2nd. And again, we have multiple options on how we could go through this. We could multiply the numbers together, multiply the x's together, then multiply the y's together, find out what our answers are. You could decide to work with the negative exponents first, rewrite these things, meaning we rewrite these things, and then multiply them together. That's a perfectly viable option also. And anything else in between there. There's a few other things that you could do if you wanted to, but those are our two main ones that we can use. Now for this problem, I'm going to elect to, because I have everything multiplying, I'm going to leave everything as multiplying together for now. And then I'll work with fractions if I have negative exponents showing up later on. But again, I'm going to do numbers, x's, and y's multiplying together first. So numbers, 3 times negative 4, it's going to give me a negative 12. X to the negative 5th times x to the 4th. The bases are the same, and they are adding together. So I have x to the negative 4th, or negative 5th plus 4. And then lastly, I have y to the 7th times y to the negative 2nd. The bases are the same, which means the exponents are going to add together. So write each of those out. Let's simplify it down. So I'm getting x negative 12, x to the negative 1st power, y to the, what's it going to be, 5th power. Okay. Now we are not done because we know how to work with negative exponents. So we cannot have negative exponents in our final answer. What is the base of this negative 1 that's here? It's that x value. So that x is going to go from the numerator spot into the denominator spot of our fraction. So let's just move down there. We could write x to the 1st power with that, but again, it's not required. And we can leave our answer just as it is right here. So again, multiple options that we can go through and solve these things. It's just one of our methods, one of our processes for making that happen. So it should be noted as you're going through all of these problems, whether it be on the homework, whether it be on the test, whether it be in future sections, future classes, there are multiple ways to go through and solve and simplify each of these expressions given to us. Jumping us back to our notes, I would highly recommend, if you're looking for a cheat sheet or anything like that for a homework or a test or anything like that, page 766 in the textbook, which has all of these properties in it as well. I would highly recommend you take a look at these and you get these nailed down for yourself. You will absolutely need them. So moving us over to our second part of the 6.7 material, working with scientific notation. And scientific notation, the main idea behind it is it's a quicker way of writing extraordinarily big or extraordinarily small numbers. So we don't have to actually put a bunch of zeros at the very beginning of a number, at the very end of a number, depending on what we're working with. So we're going to go through our two different ways of writing these things out. And our first one is going to go from decimal notation, which is the one that we are normally used to seeing, and converting that into scientific notation. Then we'll go through the reverse as well. So in general, a number is expressed in scientific notation when it is of the form a times 10 to the nth power. We're assuming a to be a number between 1, it's greater than 1, greater than or equal to 1, I should say, and less than 10. So it can be a decimal. It could also, in some instances, even be a negative number, which is perfectly fine. But the a value has to be greater than or equal to 1 and less than 10. So it could be 9.999999, go on forever. As long as it is less than 10, it's fine. And then the n value we have up here is going to be an integer. It can be a positive, it can be a negative, it can be either one of those. This is our general form that we have for the scientific notation, or our way of writing this thing out. So first and foremost, converting from decimal notation into scientific notation. So decimal notation is what we normally write things in. Scientific notation is this new one that we have here. So first and foremost, move the decimal point so the first factor is greater than or equal to 1, but less than 10. So the factor is the part that we mean here, is we're basically creating our a value up front. And again, that needs to be greater than or equal to 1 and less than 10. So we're just moving the decimal point. Count the number of decimal places, n, that the decimal point was moved. So if I'm moving it 4 spaces, then we're keeping track of that 4 spaces that we moved this thing. Write down the number as a product to the power, or as a product with a power of 10. Meaning I'm going to have the number that I created in part 1 times 10 to the, and then we're going to determine, is it going to be a positive n or is it a negative n? So here's how we're going to figure that out. If the original number is greater than 1, meaning we had a very large number, then the power of 10 will be 10 to the positive n power. If the original number was a number between 0 and 1, meaning a very, very, very small number, then the power of 10 in our scientific notation is going to be 10 to the negative n power. And we can check this by plugging things into our calculator if we need to for that. So we'll go through our two examples of converting something from decimal notation into scientific notation. So these are the two examples that we're going to be referencing over on our Blackboard. So make some space here. Okay. So we're converting from decimal notation into scientific notation. So our first example, we're starting with the number 48,300. I'm going to move us down below here just so we have our original number and then our modification to this number. Oops. So the decimal is implied to be right here, the decimal point. So our first step in the process, move the decimal so the first factor is greater than or equal to 1, but less than 10. So I want to move this thing so I get create a number that's greater than or equal to 1 or less than 10. Move this thing over to here. And what that creates is the decimal 4.83. Step 2, count the number of decimal places, n, that the decimal point was moved. So I moved it over 1, 2, 3, 4 places. So we can make a little note for ourselves off to the side that our n value is 4. And now I need to determine, is this going to be 4.38 times 10 to the 4th power or 10 to the negative 4th power? And again, the way we're going to determine this, if the original number is greater than 1, then the power of 10 will be 10 to the nth power, the positive nth power. So our original number was 48,300, which is greater than 1, which means that for our final answer, it's going to be 4.83 times 10 to the positive 4th power. We have there. Let's make that a better 4. My pen is going to cooperate with it. There it goes. So I have just converted 48,300 into scientific notation. Taking a look at our second example that we have. We are working with the instance where we have 0.0129. And I want to convert this into scientific notation. So again, just rewriting my problems when I'm moving things around. I'm good. So I want to move the decimal point so that the first factor is greater than or equal to 1, but less than 10. So I'm going to start with my decimal. I'm going to move it over to here. So that gives me a new number of 1.29, which is a number greater than or equal to 1, but less than 10. Step 2, count the number of decimal places, n, that the decimal was moved. So we moved this thing 2 places. So we have an n value of 2. And now I need to determine, for step 3, am I going to have this written as 1.29 times 10 to the positive 2nd power or the negative 2nd power? And the way we do that, again, we're checking. If the original number is greater than 1, then the power of 10 will be 10 to the n power, means it's going to be positive. Well, our original number is not greater than 1. Our number is between 0 and 1, which means that the power of 10 is going to be 10 to the negative n power, which means for this, our answer is going to be 1.29 times 10 to the negative 2nd power. And we have our final answer. So the process, I think, going from, again, our decimal notation into scientific notation, it's just a little bit of counting. It's keeping track of what did we start with, what are we ending with, and then that's kind of about it. There's not really a whole lot else to our process. We could have some different numbers showing up. We could have a different number of decimal places that we're counting to. We could have a different direction that we're counting to. But all the same, this is our process for going through and converting from decimal notation into scientific notation. So jumping us back over to our notes, we're going to work with the exact opposite now, converting from scientific notation into decimal notation. So first and foremost, determine the exponent n on the factor 10. So determine what that number is, because that's going to be crucial. We're going to move the decimal point n places, and we're going to add in zeros if need be. If the exponent is positive, we're going to move the decimal point to the right that many places. If the exponent is negative, we're going to move the decimal point to the left that many places. And then we can check our final answer. Any blank spots that would show in as we move this decimal point around, we will be adding zeros if need be. So these are 2 examples that we're going to reference. So we're starting with this one over here, so then we'll go to this one. But these are our two examples that we're going to go with for going from scientific notation into decimal notation. Come on, there's the pen going. Okay, so our first example, we're working with 9.25 times 10 to the 4th power. So again, we have our original thing here. Let's start with writing out that number out front first. That's the one that we're going to need. So 9.25. Now our problem tells us, or process tells us, I should say, determine the exponent n on the factor 10. So the exponent is 4. So we're going to move this decimal 4 places. Are we moving it to the left, or are we moving it to the right? And the way we determine that, if the exponent is positive, move the decimal point to the right. So I found my decimal point. I'm going to move it 4 spaces to the right. 1, 2, 3, 4. New decimal is there. I have 2 blank spots in here now, and I'm filling those in with zeros. So what is our new finalized answer with this? If I've converted from scientific into decimal notation, it's going to be 92,500. And there we have our final answer. Looking at number 2 with this, we're working with the instance where we have 7.5 times 10 to the negative 2nd power. So again, our process says determine the exponent n in the factor of 10. So that n value is 2. Now we need to determine, is that 2 a positive or a negative value? And we've got that negative sign there, so it's a negative. If the exponent is negative, we're going to move the decimal point to the left n many places. So again, write it out for yourself. I'm starting with 7.5. I am moving 2 decimal places, and because I have a negative exponent, I'm moving 2 decimal places to the left. So I'm counting over 1, 2, new decimal point there, fill in some zeros, and we have our new final answer, 0.075. So this is our process for converting back and forth between our scientific and decimal notations. It's essentially you're moving the decimal point left or right in either of those two forms, or depending on which version you're looking at it or you're starting with. You're moving the decimal, keeping track of that, and then writing out times 10 to an exponent, or just moving the decimal point, putting in some zeros, and then calling it done. So the last part we want to get to with this section is multiplying and dividing with the scientific notation. And I think this is a part that looks and seems deceptively difficult, or deceptively easy, I should say. It looks harder than I think it actually is. And we'll see how this pans out with this. So again, our main base definition of the scientific notation is a times 10 to the nth power. So we're going to, as a generality with this, we're going to do the specified operation with the leading a value part. So if I'm multiplying things together, I'm going to multiply them. If I'm dividing things, I'm dividing them. Then we're going to do the same operation with the 10 to the nth value part. So essentially, again, we're doing all of this, as tends to be the case with math. We're solving these problems in parts. If you do them in parts, it's significantly easier for yourself. And then we're writing our final answer in scientific notation. So our two examples, or two main parts and ideas we have with this, is if we are multiplying these things. So I have a times 10 to the m times b times 10 to the n. multiply the leading parts first. So A times B. Whatever number that would be, that's going to go out front. It's going to be AB. Then I have 10 to the m times 10 to the n. The bases are the same. They are multiplying, which means the exponents will add together. So I'm going to get AB times 10 to the m plus n power. That's for multiplication. It's for multiplying scientific notations together. If we're dividing using division here, we have A times 10 to the m divided by B times 10 to the n. You could rewrite this for yourself as a fraction. This is where fractions are very, very nice and handy for us in this regard. Similar to multiplication, A divided by B, it's going to give us A over B, whatever that number is. And then we're going to get times 10 to the m minus n. The bases are the same and they are dividing, which means the exponents will subtract from one another. So we're going to go through two examples of this, and I think we're only going to go through the division ones because the division ones are significantly, they look much harder than they really are. Multiplication, we're just doing that in parts. We've done this actually quite a bit leading up till now. And instead of having multiple variables, we're just going to now have a 10 in there. So these are the two examples that we're going to reference. We'll go jump over to our Blackboard and go from there. So our first example that we have was 8 times 10 to the 4th divided by 2 times 10 to the negative first. There we go. So again, work with this thing in parts. Work with the numbers, then work with the tens. Sounds weird to say it like that because of both numbers, but work with the 8 and 2 and then the 10 to the powers. So you can also, and this is one thing that I've found is really helpful for people, is actually write these things separated out. 8 divided by 4 times 10 to the 4th divided by 10 to the negative first. You don't actually have to write it out this way, but it's your call. And I should realize I should write that 8 over 2 correctly. I'm spoiling the rest of the problem. So 8 divided by 2, that's going to give us 4. Times 10 to the 4th divided by 10 to the negative second. The bases are the same, and they are dividing, which means the exponents are going to subtract from one another. So I get 4 times 10 to the 5th power. I can't do anything else from here. I am done. Taking a look at our second example. We have 12 times 10 to the 2nd power over 4 times 10 to the negative 2nd power. And again, as you're going through these things, I would highly recommend separate this out for yourself. 12, not 11, 12 over 4 times 10 to the 2nd over 10 to the negative 2nd, and solve these in parts. So 12 divided by 4, it's going to give me 3. 10 to the 2nd divided by 10 to the negative 2nd. Again, the bases are the same. I'm spoiling it again. Bases are the same. They are dividing, which means the numerators will subtract from one another. Numerator minus denominator. So I'm getting 3 times 10 to the negative times a negative is a positive, which is going to give me 3 times 10 to the 4th power. I can't simplify this any further because we want our answer in scientific notation, if it's starting in that. Or if the problem says to write our answer in scientific notation, then we need to do that. But we have our final answer here. We work with the numbers, and then we work with the tens to a power. So again, separate these things out, work just with the whole numbers out front, and then work with 10 to the whatever power that's been given to you. I think the part that trips people up when we're multiplying or dividing these things is we try and deal with one of the numbers and one of the tens, and then the other number and the other 10 all at the same time. And it becomes a mess that way. So again, I'd recommend work with the regular numbers and then work with the 10 to whatever power they're working with after that. I think separating those parts out and doing these things in pieces makes it a heck of a lot easier. So this is everything that we have for the 6.7 material. Again, we went through converting between decimal and scientific notation. We have with both of these. And then we worked with multiplying and dividing them out. And again, like we did with division, apply the same thinking for multiplication. Okay. So that is everything for the 6.7 material.